So question 1, what is happening within the portion labeled X? What's the term for that, right? So what's happening here is that we are having what's happening within the portion labeled X. What's happening here is that the velocity profile or the velocity distribution is still changing, right? So let's see. What's happening there is that the velocity profile is changing within that particular region or the portion X, right? And then we call that X to be obviously the entrance length, right? So now we're going to explain why it is so, right? So now we know within that particular region the velocity profile is changing, and we see that X length is what we call the entrance length. So now let's go into it and see what's happening, right? Okay, let's do this. We have more space. Okay, so what's happening here is that if you understood the basics we've been doing so far, this one here is a plate, right? Let's even say it's a cylinder, right? If based on the coordinate system here, we'll clearly say that's a cylinder, right? Because we have X, R here, and then we have Z here. So we could say that it's a cylindrical coordinate system, right? Okay. And then what's happening is that this is the fluid outside this cylinder here. So there's the fluid outside the cylinder here before it enters the cylinder. And this arrow that we are seeing here is basically describing the profile of the fluid, right? And if you've been doing a bit of physics, or maybe you are seeing diagrams, you see that because the length of these lines are the same, you could clearly see that the property, whatever the property within that region, is the same. And because you're talking about velocity here, it is clear that outside of this fluid, outside of this what's the name, this cylinder here, the fluid has what we call a uniform front. So you see, there's a freehand something. So just yeah. So basically, that's a uniform front, meaning that the properties there are the same. Or because you're talking about velocity here, the velocity of the fluid outside the cylinder are the same, right? Before it enters the what's the name? Before it enters the cylinder. Okay. And what happens is that we are still talking about what this yellow things that we have here. This, so that's this, and this, and we relate it to the portion X and Y is called the entrance length, right? Okay. Okay. So what's happening here is that if you understand a few physics, you get to know that whenever two surfaces come in contact and they are different materials, there's a high chance that there will be some sort of friction, right? So here we have let's say a fluid, and here we have a solid, right? So when this fluid is flowing and gets to about here, right, and when they get to this side, what happens is that because some of the fluid, right, or a layer of the fluid, so now we are considering the fluid to be in layers. That's why we have these arrows here, right? What's happening is that because there's a boundary at this side, right, or there's a solid at this side, what happens is that the layer of the fluid here interact with the solid, and because they are attached, which kind of like is related to there'll be some sort of friction, and because of that we have what we call in fluid dynamics or in fluid mechanics, we say we have a slip effect, right? And because of that, this particular what do you call it, layer here of the fluid, or the upper part wall of the fluid, of the cylinder, right, is stationary. This lower part is stationary, and because of that, and as a result of the low slip effect, which is kind of related to friction, this ones will kind of like feel a bit want to move as how the fluid what we call the cylinder wall is moving. And because of that, as with time, they'll end up trying to assume the same velocity of the cylinder wall, right? So as time move on, or like as you change or you move in X direction, which is we have in the coordinate system here, they'll still be trying to assume more and more and more of the cylinder wall velocity, right? But what's happening within the center here is that this one right here is the one that is furthest away from the cylinder walls, right? The left cylinder wall and the upper cylinder wall and the lower cylinder wall, right? So you see that this one right here is the one with the longest arrow. So if you're talking about it in terms of velocity, you see that that one is having the longest arrow, right? Showing that the property for that, the velocity for that one is the highest, right? Okay, so now we know about that one. Another thing that's happened too is that as this happens, right, this no slip effect will be translating. We'll try to translate to the very center, right? Because here is stationary, so this one is stationary, right? So as it moves through the cylinder, as the fluid moves through the cylinder, right, this one right here will also be, as it gets more attached to the wall, it will always also be trying to, it's also attached what's it called, in contact with this kind of the fluid layer here, right? So it will also be trying to slow this one down, and it goes on that way until it gets to the center, right? So this one here, this is something else. Okay, so this one right here is slowed down by the wall. Let's use blue. Okay, so this one right here is being slowed down by the wall, right? And as we move to the center, right, this one too here is also being trying to be slowed down by this one, and this one here is also being slowed down by this one. So the which of them do you think will experience the more of the slip effect? Is one the ones closest to the wall, right? So what happens is that as you move on through the cylinder, right, so let's say this is in the x coordinate, right, sorry, the z coordinate, because the cylinder, what's happening is that the slip effect is translating to the center, is still moving. So that's why we have what we call the boundary layer. So yeah, and then this yellow demonstration here is just trying to describe the velocity profile. So it means that within this particular place it's like this, but when it gets here, we are still experiencing the what's it called, the no slip effect at the wall is trying to a bit translate to the center. So that's why we have a different profile here, right? Yeah. So what we are saying is that within this x region here, right, or this x portion here, or we call the entrance region or the development region, what's happening is that the profile is still changing, right, as a function of what? Position, right? Because you see that this is the s coordinate. So as you move on within the coordinate system or within the z direction of the coordinate system, right, it is still changing. So as such, you see that within this x region here, or the entrance region, the fluid is in what? Non-uniform condition. So this, you see, is an application of what the term that you've been, the basic concept that you've been trying to understand so far, right? Right. And then within this room, what again do you think is happening? So now we've considered position, and we are seeing that it's changing with respect to with respect to the position or the location, right? So I mean, non-uniform condition. But then if you look within this x region again, you see that if I draw a line, let's see, I can get a line. Okay, is this a bit clear? Oh. A minute. Okay, let's do this. Okay. So now if we consider a particular region, now we are considering a particular location here where for the first one we're discussing, talking about whether it's uniform or not. We're just talking about within this region X. So it's not a particular location, it's a region. But now if you consider a particular location within the fluid, or a particular line or particular lamina within the fluid, let's say about here, still within the X region, what's happening is that you see that the profile, right? Let's see. The velocity profile. What do you think is happening? Is it changing with respect to time? Do you think it's changing with respect to time? If you consider a particular location here, right? So now we've chosen a location, let's pinpoint it here. Do you think the velocity there will be changing with respect to time? It won't, right? So if it's not changing with respect to time, then we see that within that particular position there, we have a steady state condition. Steady state. So it means that if I choose another location again, so let's say if I choose here, within that particular location again, right, the velocity won't be changing. So within this x region, you see that it means that if you choose a particular region within the x region here, right, that's within here, what's happening is that within the entrance region or the development region, if you choose a particular location, the velocity is not changing with respect to time. So here we have a steady state, right, but it is changing with respect to what do you call it, a particular position, right? So a steady, here we're having a steady state within this x region here, but then we are having a non-uniform condition, right? Okay, so that's why we see here is the entrance region is still developing, right? It's still developing with respect to what? Location. So it is non-uniform, right? But when it comes to the region outside this here, so that's about from here to wherever it is, right? Here is what we call the developed region. And what's happening here is that the velocity profile, you have this profile here, sorry, you have this profile here the same throughout, right? So that's why we see it's a developed region, right? And what's happening there is that after, let's see, what is happening there is that after it has exited the entrance region, right? If we choose a particular location, okay, if I choose a particular location on a let's see, yeah, this is the particular location. If I choose this location within or along this line here, right? Okay, if I choose a particular location along this line here, what's happening is that because the velocity profiles along the line is the same, you could say that within that region, the condition that we're having there is what? Uniform, right? And if I happen to choose a particular location and I check it, so let's say I choose let's say here, and I check what's happening to the velocity that along with against time, you see that the velocity there won't be changing as well. Whatever the location that I choose, it won't be changing as well. If I choose a location, I check it, the velocity against time, it won't be changing. So that's what we mean when we say that within this region here, it is both in uniform condition and steady state condition. So if both these two conditions are met, then we see that within that region, the region outside the x side or outside the what's the name, the entrance region, and here we are talking about let's see, so that will mean that within this region here, right, what's happening is that we have what? Equilibrium condition, right? Why? Because both the steady state condition and the uniform condition are met, right? So that's why we see that here we have a equilibrium condition. Okay, all right. So now another question is saying that from the figure 1, which is what we're having here, what does it mean when this sign here is equal to this? And if you've been following, you know what these two signs means, right? So let's see. Clearly we know that this r here is basically the radius, because we have this radius here, the full radius of the cylinder, right? The internal radius of the cylinder, right? And this one right here, if you've been following, you know, is basically the boundary layer thickness, right? Which is kind of like illustrated at this side. And we know clearly that as you move within the cylinder, the boundary layer thickness increases, right? Because it's still developing, right? So that's why we have it here. So within this region, excuse me if the diagram is a bit messy, but yeah, you have to manage it. So here is this, it's increasing until it becomes the same as the radius of that. So the question is asking, what does it mean when this boundary layer thickness, right, is the same as the r? What do you think is happening? Any guess? What is happening is that when it gets there, that's when we have let's see, the boundary layer thickness here to be the same as the radius of the internal radius of the cylinder. It means that we are entering what's the name, the fully developed region, right? Yeah, so it's clear. We know from here to here is the entrance region. So the moment the boundary layer thickness is equal to this, right, it's equal to the radius, meaning that we are entering the fully developed region, and as such we are entering an equilibrium condition part of the cylinder or part of the system. Why? Because within this side here, as we said, right, the uniform condition is met, steady state condition is met. So that's why we say equilibrium. So clearly it means that within that region, so when this is equal to this, it means that we've entered, fluid has entered the fully developed region. And when it enters the fully developed region, what it means is that the system is in an equilibrium condition, right? Yeah, the fluid is in equilibrium condition. That's what it means. All right. So here we have another question. It says, describe what is happening in the diagram, right? Oh, it should be above. Yeah. So this is above. In the diagram above, right? So what's happening here is that, then again, we know what this means. This is basically the velocity profile of the fluid, right? And this is a plate, right? So basically what it means is that before the fluid encountered this lower plate here, it had a uniform front, right? Such as this. Before it got to where this plate is, it had a uniform front such as this, right? Yeah. So what's happening here is that the fluid, there's a fluid over this plate here, right? And this plate here is having a velocity of this, right? So as a result, what happened is that because of the no slip effect, this layer here that is closest to the, using this longest arrow here, which is closest to the lower plate here, is trying to assume, right, the velocity of the plate, and as such, this velocity here will be approximately the same as this 20 meters per second, right? And then the region above will have a lower velocity. So clearly, looking at the arrows, the length of the arrows, you can clearly see that as you move in this direction here, the velocity of the fluid is decreasing, right? And it's maximum here because of what, the no slip effect. So if you ask to even introduce a coordinate system in this one, it is clear that the coordinate system will be something of this sort. So let's see. Clean this. Okay, so to be something of this, what we have this, because it's a plate, we can't say it's a cylinder, so we have x here and we have a y here, right? Yeah, so this is how it will be, and this is what's happening, right? The velocity here, because of the no slip effect, will kind of be equal to the velocity of the plate, the lower plate, right? So that's what's happening. Okay, all right. A fluid is flowing through two thin parallel infinitely wide plates, right? So thin. A force and a constant force is applied to a lower plate such that it moves at a velocity v. Okay, so then draw a diagram to illustrate the fluid flow. So that will mean that we have something like this, right? There's a upper plate. Oh boy. So this is the upper plate, right? Okay, and then now we are on the A. We're just trying to what's the name? Draw a diagram to describe what's happening there. Right. So we've drawn the two thin plates, right? They are parallel. We've done that, infinitely wide, and the wide is in the sense that the wide is not in this direction, right? The wide isn't like this. That one we can't show it, but here we are showing we are looking at it from the side, right? So the wide is like the plate could be infinitely wide like this, and there's another one below it, and the wideness is in terms of this direction, right? Yeah. But we are looking at it from the side, so we don't show the wideness, but just the concept, right? And there's the force, right? Trying to show what's happening. A constant force is applied to the plate so that it moves at a velocity, a particular velocity. So there's the force. So as such, we have a velocity v, right, which is not set, right? So now we've illustrated everything. So introduce an appropriate coordinate system. Because there are two plates, what do you think the coordinate system will be? We'll have something of this sort, right? So we have an x here, we have a y here. It could be it's actually a rectangular coordinate system, right? And show the direction of the applied force. We've shown that, which is this, has a velocity v, right? And now we are asked to show what's the name? The direction of the momentum flux. Before we do that, we have to show actually what's happening to the fluid, right? So let's see. Before the fluid enters, it will be something of this sort. Let's see. Let's try and get something from here. Oh boy. Good. So before the fluid enters, it will have a uniform front like this. Okay. Nice one. Right? And when it enters, the fluid within this particular two plate here, what happens is that we'll have something like this. Okay, so if you post it here, let's see. It won't be as what's happening on the inside. Right? So now we're just looking at the laminates within the fluid, but we'll look at it at the molecular level as well. Right? Okay, and we'll have this one sort of here. Let's move this more. Okay, and we'll have this here. we'll have this here. This is a bit manual, but if you have a particular video showing it, that will be way more better. But here we're just trying to use diagrams to show what's happening, right? Okay. And so because of the velocity here, and then because of the no slip effect, the fluid closest to the wall, right, or the thin plate at the lower wall will try to assume the velocity there, and as such, the velocity of that one will be highest compared to the rest, right? So that's what's happening. Okay. So we have this, right? But if you look at it at the molecular level, what happens is that if we have molecules of fluid, molecules of the fluid, so let's say we are using balls to kind of like describe that, right? So if we have something like this, let's see, we're going to give each layer a different color so we know what's happening. So this is basically the, so here what's happening here was that when we're doing this, we're looking at it at the macroscopic level. We're just seeing the laminars, right? But if you're using the what do you call it, the boys here, are basically doing the micro, right? This is how we are illustrating it here. It could be different somewhere else, but for understanding that we are doing it this way, right? So if we have it this way, okay, let's change this one. Okay. All right. Okay. So this is basically the molecules of the fluid. So what's happening is that because these molecules of fluid are the ones closest to the wall here, their velocity will be the highest. So let's say comparing the velocity, right? There are three, right? So we have the yellow, and then we have the blue, right? And then we have the brown, right? So in terms of velocity, what's happening is that the velocity of the fluid or these layers, the yellow is the greatest one, right? The yellow will have the greatest velocity. The yellow layer of fluid will have the greatest velocity, followed by the brown, right, and the blue. Why? Because of the band, what do you call it, the no slip effect, and the ones closest to the plate, right? So these ones are closest, so they will try to move as much as possible as close to the velocity of the plate, right? This one will try and move as close as it can. The layer here will try and move as close as it can to the velocity of this one, but still be lower. And then this will try to move closer to this, but still be lower, right? So basically because of the, what's the name, the no slip effect. So what's happening here is that the velocity is diffusing, right, in this direction. So diffusion means I'm moving from a high concentration area to lower. And because we know that the velocity, this one here is the velocity in the yellow layer is greater than this, and the one in the brown is greater than this, the diffusion will happen in what direction? This direction. So that's what we mean by the direction of the momentum flux, right? So because it has a velocity, it will have what? A momentum. Because you know momentum is equal to mass. Let's make it capital M, capital M. Right? Because you know momentum M is equal to mass times velocity, right? And because these particles have a particular mass, they'll try and transmit this momentum, right? And we see that flux basically means that a quantity per cross-sectional area, right? So this basically here we having two plates, but then if you look at the cross-sectional area, it could be some sort of a triangle because of the space between them. And because we are saying they're infinitely wide, that will mean that if you're looking at the cross-sectional area, it will be very wide, infinitely wide. This is a cross-sectional area, right? And here will be let's see, this side will still be a y. Yeah, this side will still be a y, right? But we are not seeing the x here. The x is not visible here because you're looking at the cross-sectional area, right? So that will mean that the momentum is diffusing up. Why? Because you see that the momentum here is directly proportional to velocity, and since the velocity here is diffusing in this direction, as we see here, right, that it also means that the momentum as well too will be diffusing in this direction. So the flux is basically concerned with the area, right? A particular rate changing with area, right? Cross-sectional area, right? So the momentum flux is also this direction of the momentum flux. So yeah, so this arrow here will be a direction. Might not fit there, but I'm going to write it anyway. Direction of momentum. Forgive me that I don't feel. Let me write it. So this arrow here shows direction of momentum flux. Let me zoom in and write it. So it goes. So direction of momentum. It's not fit. But you know what I'm talking about, right? So this is the direction of let's just say flux. But here we know it's all momentum flux, right? So now we've answered all the questions, right? So it depends on you. You can choose to use the arrows to illustrate that, microscopic, or you can choose to use the molecules to represent that, microscopic, right? All right. So the next question says state. Oh boy, something has moved. Oh, let's see. Okay, a minute. Change something first. All right, I think that's fine. Okay, that's fine. Okay. The next one says that state Newton's microscopic law of viscosity, right? So as we were saying, this law is basically derived using this diagram that we have here. It was derived using this, right? So because we are stating, we're not explaining, we've already explained everything we need to already. So let's see. So the microscopic is of this sort. That will mean that we have right, cross-sectional area. We go to viscosity, right, and then we have velocity, and then we have y, right? Yeah, based on this diagram that we have here, it could change depending on the coordinate system, but because we are talking about two plates here, this is how to be, and that's the general one, right? And define each term. Here we know this to be the force, right? We know this to be cross-sectional area. We know this to be viscosity. What type of viscosity? Dynamic viscosity, right? This is velocity, and then this is what's the name? Distance from the origin, right? But if we try to describe these two terms as one, right, together, we call this what's the name? Velocity gradient, right? Velocity gradient, right? To describe each term. And the microscopic. The microscopic is of this form. We have this, right? And then the coordinate system could be anything. So let's leave it blank. And then we have a minus, and we have viscosity, and we have the V. The let's make it Y here. Let's make it Z. Assuming that we are in a cylindrical coordinate system, right? Yeah. So this time here is the shear stress. This is viscosity, dynamic viscosity. This here is also the velocity gradient, right? But another question: why do you think we have we have a negative in the microscopic one, right? Because looking at it, they should be similar, right? Yeah, similar. So looking at this, these ones are related, right? And this is related. Oh, let's skip the negative. This is related to this, right? And this one as well too is related to this, right? So why the negative? Now let's go over this one more time, right? So now let's clean this. You can skip this side if you don't need it, right? This is open. So clearly we are even using this diagram here. Let's use this. Okay, so we can use this to talk about the velocity profile. So okay, so that we have this and we have this, right? Let's consider here. So looking at this, for instance, you can see that the velocity within this side is different from the velocity here and the velocity here and the velocity here, right? So basically this here is what we call velocity profile, right? Which would be the same. So this is the velocity profile or velocity distribution, right? Okay. So what's happening here is that we know that clearly the velocity is decreasing in that direction, but when we are trying to do this using calculus, what happens is that if because our coordinate system is in this direction, we do it with respect to this, right? So that will mean that This the V, the Z here is something of this sort. Okay, now let's change this because we are using that example, right? That will mean that here is what? Y. Change respect to Y, right? Okay. And as such, if you are trying to rewrite this based on this diagram, it will be let's see. Okay, it will be shear stress in the X direction, right? But changing in the Y direction. Yeah. So definitely this change based on the coordinate system that you have or the system that you have, right? Okay. So looking at this very well, if we are doing this, you see that in this direction like this, right? In this direction, the Y is what? Increasing, right? Y is increasing. So basically we are trying to see what's happening to this V here. Let's see something else. We're trying to see what's happening to this velocity here against V, right? So you clearly, based on the coordinate system, we know that Y is what? Increasing in this direction, right? But what do you think is happening to the V? The V is basically what? Decreasing, right? So if the V is decreasing, we are saying this whole thing here, this is the velocity gradient. To mean that this velocity gradient will be becoming more negative and more negative, right? It will be decreasing. So if it's increasing, it's positive. But if it's decreasing, so this is increase, right? Negative means what? Decrease, right? And since this velocity gradient here is what? Decreasing in the direction of Y, that's why we have the negative here. So basically this negative here is because of this velocity gradient. That's why we have this negative here, right? So if this is negative, and we know shear stress is not a negative something, right? And because this is negative, we have to introduce a negative sign here to cancel the negative because of the velocity gradient to make this shear stress positive. So that's why we have the negative here, there, right? So basically this one here is so question 7, right? This is shear stress in Z direction that is changing in Y direction, right? Yeah, so that's what that one means. So question 8 says what's the name? Tau YZ is equal to tau ZY, true or false? As in something's missing. Let me introduce here. Always, right? It's part of the question. So tau YZ is equal to tau ZY, always, true or false? What do you think? And the answer is it depends, not always, neither. So basically it's neither true nor false, but it depends on the system. So if you have a system where the fluid is flowing, so looking at this one for instance, we know the fluid is flowing in this direction, right? So meaning that we are basically having we are experiencing the shear stress. The fluid will be flowing in the X direction, right? But we'll be experiencing the shear stress will be changing within the Y direction, right? So that's for this particular system. So it's not always the same. It depends on the system, right? So it's not always the same. So that will mean that because of that, okay, this one is saying always. Because of that, the answer will be what? False. Right? So the answer will be false here. So the answer will be false. And that's the explanation. It depends on the coordinate system. And using this one for instance, the fluid is flowing the X direction, right? But the momentum is changing the Y direction. The velocity is changing the Y direction. The shear is changing the Y direction, right? So basically, if you consider this cross section, right? So if you take a cross section here, and let's say we have the fluid like this, we have the bulk fluid to be something like this, right? So now we are considering a volume of fluid, so something like this that's flowing through, right? So before it enters those two parallel plates, we have the fluid to be like this, the volume of fluid to be like this. But the moment it enters, right? When it enters the original between the two plates, we have something like this, right? We have this, and then let's see. Okay, so we have this, and then we have this, right? Oh, okay. This, and then this. Why? Because we are experiencing this force here. So this shear force here is sharing the downside, right? Sharing the downside. So basically, we will put the velocity profile here. This. Alright, so there's a shear at the downside because of the what? The lower plate, right? Yeah. So that's what's happening. All right.